Okay, hey, what's up? We're going to start talking about Chapter 17, a couple different probability models. So let's go ahead and start to look through our notes here. We have Bernoulli trials, which is basically what this entire chapter is about, a couple different models that we use that are Bernoulli trials, and there's a couple things here that we need for that to be true. In a Bernoulli trial, it has to either be a success or a failure. For each trial. So it has to be just winning or losing, success or failure. No, it's not a matter of maybe winning one game out of two or something like that. Like each outcome has to be success or failure. And then you can combine those different ways, but the two outcomes. The probability of success, let's call that P, is the same. It doesn't change. And if the probability doesn't change, the trials are independent. Okay, so independent. So those two kind of go together. If things are independent, then they don't change the probability of each other, and so the probability of success will be the same. Will be P for every single one. That'll just repeat and repeat and repeat. Some situations that we have are not independent. We kind of pretend that they are, and just for the sake of using an easier model, as we're taking cards out of a deck, the first card's out of 52 because there are 52 cards, and if you remove one of the cards, now it's out of 51. It changes it a little bit, but not much. It only changes it just a little bit. So we're going to say this is overridden by the 10% condition. Which is basically saying if you don't take more than 10% of the population, it doesn't really change enough for it to matter in the end. So with the playing cards, we can take about 5 of them out before we're beyond 10%, and then the denominator will really start to change in a way that's significant. So the 10% condition is what we just, we can do these without replacement, but we just have to make sure we don't take more than 10% of whatever is there. It's more sample than 10% of your population. So let's look at a example here, number 1. New sales gimmick has 30% of the M&Ms covered with speckles. Ooh, shiny. These groovy candles are mixed randomly with the normal candies, and they're put into the bags for distribution and sale. You buy a bag and remove candies one at a time looking for speckles. Is this situation a Bernoulli trial? Well, we have our 3 criteria. Let me look. Okay, success or failure, and then we need a probability, and we need the trials to be independent. So do we have success and failure? I'm looking for the speckles, so let's see if we can define it. It's there. Success is a sparkly what is it called? Speckles, yeah. Sparkly M&M, I'll just go with that. And failure is a normal M&M. Okay, normally I wouldn't say a normal M&M indicates any sort of a failure. It's still delicious and wonderful. But for our definition, for what we're doing here, we're saying that getting a normal M&M is a failure. So we have a success and a failure. That's good. What else do we need? Let me see. We need a probability of success. Success is 30%. The probability is 0.3. That's I like a lowercase p. Doesn't really matter, but I like it. So that we have probability. And let's see what else we have here. The trials are independent. These are not independent. When I take one M&M out of the bag, it will change what's in the bag. It will change the population that I'm drawing from. So they're not independent, but as long as we don't take more than 10%, we can just assume they're independent for the sake of simplicity. My hair is really doing something there. Oh well, I'll just go with it. Woo! Anywho, I just noticed that. Okay, so not independent. D-E-P-E-N-D-E-N-T. But okay, as long as we don't take more than 10%. Okay, good. Okay, what is the probability that the first speckled candy is the fourth one we draw from the bag. So even though we're not dealing with replacement, we're going to kind of assume that probability is going to stay the same. We're going to also assume we're not going to go beyond 10% of the bag to get away with that. So we're keeping these thoughts, these assumptions in the back of our mind as we do this. So what's the probability that the first speckled candy is the fourth one we draw from the bag? Well, let me see. That's going to be, well, first off, the probability is 0.3, and the probability, hang on, probability of success is 0.3. Failure is 1 minus 0.3. So the probability of failure is 0.7. So failure is 1 minus whatever p is. Let me make that a little more beautiful. Awesome. Okay, so success is just the probability, and the failure is the complement of probability, or 1 minus the probability. So that gives us 0.7. So the probability of first speckled candy is the fourth one we draw from the bag. So I want 3 failures, and then I want success. So I want my first one to be a failure. That's 0.7. And then I want my second one to be a failure. And then I want my third one to be a failure. And finally, I get to the fourth one, and I want this one to be the, let me see, I want this fourth one to be the first speckled candy. So this will be 0.3. And that comes out to, and that comes out to, I know, quite a, I would assume that it would say to multiply if I didn't put anything. Let's go ahead. Oh, there we go. Use multiplication instead. Woohoo! 0.1029. 0.1029. Now we could shorten this up a little bit, and I guess I could say the probability that the first speckled one is the fourth. There we go. We could shorten this up a little by using an exponent. So I could have just said it's equal to 0.7 to the third power. Let me see if I remember how to do that. Beautiful. Times 0.3. Whoops, let me undo that now. Awesome. It's a Command-Shift plus on a Mac, and get away from your bug. Control-Shift plus, I think, on a PC, something like that. You can Google it. So to make that superscript, that exponent up there, so 0.7 to the third power times 0.3 gives you that 0.1029. So a little more than 10% of the time, the fourth one will be the first speckled one I draw. Okay, this next problem is pretty similar. Let me go ahead and just copy and paste that. Copy, and what's the probability? We're going to move it to the 10th one. There we go. It almost messed up my numbering there. The first speckled one is the 10th. And I have to write out a bunch of these 0.7s, so let me just skip that one. I'm just going to borrow from my next line there. Awesome. Okay, so 0.7, the first speckled one is the 10th. So the first 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, have to be failures. So this is going to be to the 9th power, still times 0.3. So the first 9 right here are all failures. The first 9 are all 0.7s, and then just the 10th one is that 0.3. So that gives me all 10 trials, and let me see my friend here. 0.7 to the 9th times 0.3. I should just let the bar come up down there. 0.0121. I'll round it off there. 0.0121. So there we go. The probability is a little more than 1% for that one. So the fourth is a little more than 10%. The 10th is a little more than 1%. So it's 10 times more likely to happen in the fourth than the 10th if you're just comparing those two. Okay, we're moving along here. Write a general formula. All right, let me see. General formula. Let me go ahead and write this in terms of our random variable. And in fact, I might go back and edit those as well. X equals, and we'll say k is our number. Let me go back here. For the first speckled one to be the 10th, maybe I should have written, and we can just add in here if you're following along your paper, which hopefully you are, otherwise I don't know why you're watching this. So the probability that my random variable equals 10, my random variable being when I see the first speckled candy, is 0.7 to the 9th times 0.3. So when x, let me get rid of this as well. I don't need you. So the probability that my random variable equals any number is, well, let me see, for 10 it was 0.7 to the 9th. Those are the first 9 there. And then the 10th one was right there for my 10 trials. So here, this will be 0.7 to the, if it's k, it's going to be 1 less than that. K minus 1, and then times 0.3. So that will do it for this particular instance. We can also think about, let me make another copy of this. Oh, please stop doing that. Oh, well, can I tell you to stop creating automatic? Oh, well, I'll get there. So let's see here. The probability, well, 0.3 was my value for P. Let me go back up here. 0.3 was my value for P, and failure, that 0.7, was 1 minus P. So I can also generalize this a little bit more. I can put both of those values in there as well. So 0.7 is 1 minus P. Okay, so this is a general formula. Let me make that awesome. Can I center it? Goodness. That was pretty awesome. Okay. So my awesome general formula is the probability that x equals some number, my random variable, when I see my first speckled candy or when I see my first, I don't know, widget coming off the factory line that doesn't have the right widget-esque on it, or whatever. The probability is 1 minus the probability to the k minus 1 times P. And I'm going to give you yet another version of this. And let me go back up to add something to our notes there, and then I'll fix this here. This is super annoying, having to write my failure is 1 minus P, because we end up writing, we end up writing 1 minus P a lot, and if it's to an exponent, you always have to put parentheses around it. If you're multiplying it by something, it's a real pain to have 1 minus P, writing that again and 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 again. In parentheses. Let's just call it something else. So let me go back up here. I'm going to add something to this line. For failure, I'm going to say for failure, we are just going to call it Q. So when I put a Q, I'm talking about this 1 minus P. I don't really need another variable. It's just really, really, really super helpful to not have to write 1 minus P so many times. So let's go ahead. I'm going to make one more copy of this. Did I do it? Oh, I crashed Word. Hang on. I'm just copying and pasting. It should take up a lot of processor power. And basically, I'm just going to replace the 1 minus P with a Q. So it'll be Q to the k minus 1 times P. Let me try to save. Come on, Word. It recovered. I know, this is great TV, right? There we go. Come on. It recovered some of it. Let's just go ahead. What's the probability we find the first speckled one after the first? right? A general formula. Here's where we were. So the probability of our random variable being equal to some number k is equal to the failure to the 1 minus k power, okay, times the success. So the probability that the first success is at k is, whoops, k minus 1. Goodness gracious, that was terrible. Good thing I double checked. So the probability of, if I want the first success to be on k, the first k minus 1 trials, so if I want this to be 10, it'll be the first 9 trials or failures, and then 1 success at the end. So that is our general formula. For E, what's the probability that we find the first speckled one among the first 3 that we look at? Well, let me see. I think this is one where it'd be a lot easier just to use the complement, right? Because the first speckled one is among the first 3. There's lots of different ways that can happen. You can have the speckled on the first, and then other stuff happening. You have the speckled happening on the second, and then maybe the third. Let's just find the complement. 1 minus the probability of no speckles on the first, within the first 3, in the first 3, among the first 3. Okay, so 1 minus failure, failure, failure. 1 minus q to the 3rd power. And just start thinking of that letter q as a failure. 1 minus q to the 3rd power. So that will be 1 minus 0.7 to the 3rd power. There we go. 1 minus 0.7 to the 3rd power. So that is what that would come out to. And let me, just for fun, it's always good to see what that is. 1 minus 0.7 to the 3rd power. Oh boy. 1 minus 0.7 to the 3rd power. It's going to give me 0.65. Probably one more. 0.657. Okay, so the probability that we find the first speckled one among the first 3 is at 0.657, 65.7%. Oh my, no speckles, no speckles, no speckles. Yes, good. Okay. Sorry, just double checking myself. And how many do we expect to have to check on average to find a speckled one? And let me just tell you what this is. The expected value, we're going to talk more about this definition of geometric distributions. This is a geometric distribution. And if you have taken Algebra 2, I know some of you are in it right now, but a geometric distribution basically multiplies by some number each time. You know, you have arithmetic and geometric multiplies each time. And so this is a geometric distribution, and anytime you have a geometric distribution where you're multiplying, let's look at our formula here. You know, as k increases, you're multiplying by another q each time. So basically, as that happens, if you have that case that's geometric, and the expected value, whoops, is always going to be just 1 over p. And we'll talk more explicitly about that in a minute. In this case, it would be 1 over 0.3 is 3 and a 10/3 or 3 and a 1/3. Okay, so that's the expected value. We'll get more into that definition in a little bit. And don't worry about how we came about that. There's a math box in the book that goes over how the expected values and standard deviations come about. But for our purposes in class and what you'll need to know in the end, you won't have to derive that. So that is the end of the first part of this video.